Hello everyone, this is Ketish here. In this video, I'm going to go through question number 11, 12 and 13 from the AQA Physics Specimen paper, one higher tier. Question number 11 is on the topic of energy. Figure 17 shows a student before and after a bungee jump. The bungee cord has an unstretched length of 20 meters. So the diagram shows the bridge, the student standing before jumping. From the waist to this dotted line is 20 meters. Now, after the person jumps, the lowest point that the bungee cord, the maximum extension or length it's going to go is 55 meters, which is much safer from the water level. The mass of the student is 50 kilogram. The gravitational field strength is 9.8. Write the equation which links gravitational field strength, gravitational potential energy. So gravitational field strength is G, gravitational potential energy is EP. If you look in the equation sheet or generally in the classroom, we write GPE. Height is H and mass is M. So what is the equation that links all of it? You can write it as GPE as well, it's fine. Gravitational potential energy equals the mass multiplied by the gravitational field strength multiplied by the height. You can write the symbol equation, which is, we use a different color, GPE equals mgh. Calculate the change in gravitational potential energy from the position where the student jumps to the 20 meter to the point 20 meter below. So the potential energy or gravitational potential energy, mass is 50 multiplied by 9.8 gravitational field strength multiplied by the height, which is 20. That's 9,800 joules. Question 11.3. 80% of this change in gravitational potential energy has been transferred to the student's kinetic energy. How much has the student's kinetic energy store increased after falling 20 meters? So how do you find out 80% of 9,800? So 80%, if you divide it by 100, is 0.8. Multiply that by 9,800. That gives me 7,840. Calculate the speed of the student after falling 20 meters. Give your answer to two significant figures which carries a mark here. So the kinetic energy, EK or KE, equals half times the mass multiplied by the velocity squared. We are trying to find the velocity here. So we are going to use the kinetic energy, which is 7,840 equals 0.5 times 25. Oh, sorry, not 25. Times 50, which would give 25 times V squared. So V is 7,840 divided by, if I do the maths here, 0.5 times 50 is 25. Now, because it's squared, I need to remove the square sign. So I am going to find the square root of this. And that gives me 17.70875 meters per second. Now I need the answer in two significant figures. So that would be 18 meters per second. Question 11.5. At the lowest point in the jump, the energy stored by the stretched bungee cord is 24.5 kilojoules. The bungee cord behaves like a spring. Calculate the spring constant. Spring constant is K of the bungee cord. Use the equation sheet. Now the energy is 24.5 kilojoules. So 24.5 times 10 to the power 3 joules. That needs to be converted to joules. And the equation is elastic potential energy is equal to half K E squared. Now the elastic potential energy is the stored energy. At the lowest point, the energy stored by the stretched bungee cord is 24.5. So if I 24,500 joules is the elastic potential energy. So this is 24,500 joules equals 0.5. Let's convert the half to 0.5 multiplied by the spring constant is what I'm trying to find, and the extension squared. Now remember, the length of the bungee cord is 20 meters. When the student jumped, it went up to 55 meters. So if I take 55 minus 20, that gives me 35 meters as the extension. So that's 35 squared. Rearranging the equation, K equals 24,500 divided by 0.5 times 35 squared. I think put that in it. That gives me an answer of 40 Newton per meter. Next question. Question 10 is on the particle model of matter. This is actually the required practical to find the density of regular and irregular objects. Required practical. A student wants to calculate the density of two objects shown in figure 18. You have a metal cube, which is the regular object, and the irregular object is the small statue. Describe the methods that the student should use to calculate the densities of the two objects. How do you calculate the density of the two objects? Now, you need to know the equation for density, which can be found in the equation sheet. Density equals the mass divided by the volume. So you're going to use this equation to find the density of both of them. In order to do that, you need to know what the mass of these objects are. What is the mass of the metal cube? What is the mass of the metal statue? In order to find the mass, you would need a weighing scale. If you put both these objects on a weighing scale, you can find the mass either in grams or in kilograms. And the second part to the equation is, how do you find the volume? If you determine the volume for these two objects, then you can determine what the density is by calculating. Now, to find the volume, because it's a regular object, that's the length, width, and the height. So remember, volume of a regular object is the length times the width times the height. Now for a small statue, it's very hard to determine taking measurements. For that, you would need a Eureka can or a measuring cylinder, if that object can actually fit into the measuring cylinder. Let's use a Eureka can, which is basically like this. You fill it up to with water, then you put the statue inside, or you immerse it, and any the water level is going to go up, and you collect the water that comes out in a measuring cylinder, and the volume of water collected or you could say displaced, is equal to the volume of the statue, right? That's your answer. So how do we actually write an answer for this 6-mark question? For both, measure the mass using a balance or weighing scale, and you could say calculate the density using rho equals mass over volume. Now I think this bullet point is better written before the second one. So density equals mass over volume. That equation is important. And then measure the mass using a balance or weighing scale. For the metal cube, measure length of cube's sides using a ruler and then calculate the volume. And you could say volume equals length times width times the height. Give the equation. And for the small statue, immerse in water. And they're not actually looking for in the marking scheme that whether you how you actually going to do it, but immerse in water in brackets in a Eureka can, right? Measure the volume of mass of water displaced. So better to actually say measure the volume of water displaced. Volume of water displaced equals the volume of the statue. Now I mentioned above at the start that you can use a Eureka can, but you can also use a measuring cylinder as well. So if I fill up a measuring cylinder, let's say up to the halfway point, 50 centimeter cube, and let's say the statue actually fits into the measuring cylinder, and if I put it in there, it'll sink to the bottom obviously, and the water level is actually going to go up, and that water level, the difference, the height or the volume that changed is equal to the displaced water volume as well. So you can use both ways. Next question, the last question for this paper. An electrician is replacing an old electric shower with a new one. The inside of the old shower is shown in figure 19. If the electrician touches the live wire, he will receive an electric shock. Explain why. Why would you get an electrocuted if you touch the live wire? Now the live wire has a potential difference of around 230 to 240 volts. Now our body has zero potential difference, which means current always goes down a potential difference. So the current will actually move from the wire to the person, and that would result in an electric shock. So how do you write this? Because the potential difference of the live wire is 230 volts and the potential difference of the electrician is 0 volts. There is a large potential difference between the live wire and the electrician. So the charge or the current passes through his body, resulting in an electric shock. Next part. Different electrical wires need to have a cross-sectional area that is suitable for the power output. Figure 20 shows the recommended maximum power output to wires of different cross-sectional areas. So as you can see, the cross-sectional area is increasing in millimeters squared from 1 to 16. That's basically the thickness. And as the thickness of the wire increases, the maximum power output in kilowatt is also increasing. The new electric shower has a power output of 13.8 kilowatt. Determine the minimum diameter of the wire that should be used for the new shower. The diameter D can be calculated using the equation. Now, as part of your GCSE, they're going to give you an equation that you haven't seen before in order to test that you can actually use different equations. So, A is the cross-sectional area of the wire. How are you going to find the cross-sectional area of the wire? That needs to come from the graph, and you should know the value of pi, which is 3.14. So at 13.8 kilowatt, now the x-axis is already in 30 kilowatt, so I need to find out what is 13.8. what will be the cross-sectional area. Now 0 to 2, so 2 divided by 5, because there's 5 boxes, so each box is 0.4, right? So 13.8, so that's 14 is 10. So I'm looking for one box below that. So 13.8 kilowatt is somewhere around here. Now let's say that's over there, that's 9.8 millimeters square. So let's use this in the equation. A is the cross-sectional area, so D equals the square root of 4 times 9.8 divided by 3.4. So let's bring in the calculator for this. I'm going to do this step by step. 4 times 9.8 gives me 39.2. Divide that by pi, 3.14. That gives me 12.48. So let's find the square root of 12.48. So we square root of 12.48. That gives me 3.532. So I'm going to leave it 3.53. 3.53. Now the marking scheme actually accepts an answer within the range of diameters 3.50 to 3.55. That should be fine. The charge that flows through the new shower in 300 seconds, so that will be the time, is 18,000 coulombs. That is the charge. The new electric shower has a power of 3.8 kilowatt. If I change that to watt, that's times 10 to the power 3 multiplied by 1,000, 13,800 watts. Calculate the resistance of the heating element. Now, use any equation. Write down the equation that you use. So 5 marks. Now, the equation that links power equals I squared R. Now, we don't know the current. Do we know the resistance? Not really. So, which we can't use. Let's try power equals the energy divided by the time. That I can use. I can find out the energy using the power and the time. So resistance is what I'm trying to find here. So I will need this first equation, P equals I squared R. But I need to find the power first. And I need the current as well. I can use this. Current is the rate of flow of charge, which means I equals Q over T. So let's use this equation first. So let's label that. First equation, the charge is 18,000 divided by 300. That gives me a current of 60 amps. Then I can use the power equation second. Power is energy, so actually don't need it there. I can actually go straight to this equation. Power is 13,800 equals I is 60, which we calculated here. So 60 squared times, let me get rid of this equal sign, R. So rearranging the equation, R equals 13,800 divided by 60 squared. So that gives me 3.83 ohms. 3.83 ohms. That brings us to the end of this paper. Thanks for watching. Sorry about the mistakes right towards the end. I hope you found the video useful, and this specimen paper looks like has the longest, feels like the longest. It has the 13 questions. I haven't seen any other paper since 2018 or 17 actually that has actually 13 questions. Generally most of the papers are ranging between 9 to 10 questions in each of the paper. Anyway, if you found this useful, hit on the like button, and if you are doing your GCSE, maybe subscribe, and I will be uploading videos right up to the GCSE, hopefully the 2024 paper right towards the end as well. Thanks for watching again. Bye.